In order to study chemistry, one of the things that we have to get a little bit of an understanding of is chemical elements and, more importantly, the atoms that make them up. So again, elements, we talked about this in chapter 1. Elements are substances that cannot be broken down into simpler chemical substances. Every element has some name of the element and a 1 or 2 letter symbol just as a shorthand. If you want to memorize all the elements, go for it. There's really no reason for it. In my opinion, it might win you a trivia contest somewhere, but we'll be using a lot of elements, and we'll be using a number of them often enough that you'll probably start to remember some, but there's no reason to sit down and memorize them just for the sake of memorizing. What about atomic theory? So long ago, some of the early scientists observed that, again, if we've got a sample of an element, we can cut it in half, and we can keep cutting it in half over and over again, and it maintains its identity as that element. At some point, we have to get to the smallest piece that we can still call that element. And that smallest piece, that tiniest particle, is what became known as the atom. All matter is made of atoms. Now, since then, we've learned that we certainly can break atoms down into smaller pieces, but if we break apart an atom, it's no longer the element that it started as. So whether it's zinc or copper or oxygen or sodium or argon, if we get all the way down to a single atom of any of those, if we break it down any further, it's no longer that element. Most elements exist as individual atoms in their pure state, but there are a number of elements that exist as either diatomic or tetraatomic molecules that have 2 or 4 or 8 atoms stuck together as a unit. When we see these, we're going to designate those with a little subscript, and for the most part, you don't have to worry about those except for the 7 diatomic elements listed here. So hydrogen, nitrogen, oxygen, fluorine, chlorine, bromine, and iodine are all diatomic elements. And if you see those in a problem, if you hear hydrogen, if you hear chlorine, what it's referring to is that diatomic molecule, H2Cl2, or all of the others. Now, specifically in problems that I'm making up, in problems that I'm writing, anytime I say just the element name, like bromine, I mean the diatomic element, Br2. There are going to be some very limited specific cases in this class where I actually want to talk about an individual bromine atom, not Br2, but just a single bromine atom. And I'll usually try to be really explicit about that and specifically call it a bromine atom. So anytime you hear just the name of the element for these 7, they're always going to be diatomic unless there's a specific reason in the problem for them not to be. So what do atoms look like? We might think of an atom as just an indivisible little ball of matter, and that's one of the early pictures that chemists had of the atom. It was the hard sphere model. So it's like a bunch of little marbles stuck together to make an element. But then we started to learn that there are some more subtleties to atomic structure. So first of all, there are 3 subatomic particles that we're going to concern ourselves with. Those are protons, neutrons, and electrons. Protons are, relatively speaking, large, and they're positively charged subatomic particles. Neutrons are relatively large. They're about the same size as a proton, and they're uncharged subatomic particles. And electrons are tiny. Electrons are really tiny, and they are the negatively charged subatomic particles. When we look at atomic structure, atoms are arranged so that the protons and the neutrons, almost all of the mass, is located in the nucleus. So here's a picture of just a little nucleus. That's got almost all of the mass of this atom, and then there are electrons that are kind of zipping around. One of the key experiments to show that atoms were not hard little balls was the Geiger-Marsden experiment on gold foil. So one of the advantages of gold is it can be hammered very, very thin. And it can be hammered so thin that it's 1 or 2 atoms thick. It really can be hammered that thin. So in this experiment, Geiger and Marsden took a piece of very, very thin gold foil and they shot a beam of alpha particles at it. Alpha particles, just a source of radiation. Now, if atoms were hard spheres, then we would expect an awful lot of this radiation to hit the sphere and bounce back, right? So we would have expected a lot of scattering of radiation back here. This green ribbon is their detector. But what they found was that almost all of the radiation went right through, or very close to straight through their gold foil. Some of it got reflected or deflected pretty significantly. Some of it just got deflected off to the sides. But that was how they supported the atom as a whole isn't a hard sphere, but from this experiment, we can envision the nucleus as almost all of the mass, and the nucleus is, in this model, almost a hard sphere with just a very soft electron cloud floating around it. Protons and neutrons have equal and opposite charges. So one of the things that we always have to keep in mind in all of chemistry is balancing out charges. Opposite charges don't like to be separated in nature. They tend to attract each other and stick together. So when we're looking at atoms, the protons, the positively charged particles, and the electrons have to be present in equal number if we're going to have a neutral atom. If we have a situation where they are not present in equal number, then our charge is unbalanced and we have something called an ion. An ion is any particle that has a residual charge on it. So if a species, if we've got something that has 19 protons and only 18 electrons, it has 1 extra proton compared to the number of electrons, so it's going to have a positive 1 charge. Positively charged anions, or positively charged ions, are called cations. And again, this is pronounced cation. It's not pronounced cation, but positively charged cations. Looking at the other direction there, if something has only 9 protons but 10 electrons, now it has 1 extra electron compared to the number of protons. And this would be a negatively charged anion. And again, anion, not anion. Anions, negatively charged species. So to keep track of all of these subatomic particles, we've got a few important numbers that help us do that. First of all is the atomic number. The atomic number is the number of protons, and the number of protons identifies the element we're working with. All atoms and ions of a given element have the same number of protons. So looking up at my periodic table, silicon has 14 protons. Any atom or ion that I find that has 14 protons in the nucleus, has an atomic number of 14, is silicon, always. The next important number here is mass number. So again, almost all of the mass of an atom or ion is due to its protons and its neutrons. So it makes sense that the mass number is the number of protons plus the number of neutrons. The mass number defines which isotope of an element we're working with. So all, all lead atoms have, have 82 protons, but they can have different numbers of neutrons. So if I've got a collection of lead atoms that have 92 protons and 96 neutrons, those are all one isotope. And those, what did I say, 92 and 96? 188 would be the mass number for that. And finally, charge. We kind of talked about this one already. Charge is the number of protons minus the number of electrons. And if you like a formula, you can use this formula. I like to just think about it looking at the numbers of each and seeing which one I've got extra of. So if those are balanced and if the charge is 0, we're dealing with an atom. If the charge is not 0, it's an ion, either cation or anion. One important point here, and this is going to become much more important coming up, mass number is not the same as mass. So we're going to end up talking about the mass of an atom or an ion, and oftentimes we'll find that the mass of an atom or an ion is similar to the mass number, but mass number is not mass. The mass number is the sum of the number of protons and neutrons, so it's always an integer, it's always a counting number. The mass of an atom or an ion is almost never an exact integer. So keep mass and mass number separate for you. Now, as just a little side note here, when radioactive elements are discovered, when they're first discovered, they're often reported only with a mass number because the accurate mass hasn't been determined at that point. But so sometimes you'll see some recently discovered elements just have a mass number listed. They don't have a well-defined mass. That's just because they're new, they're hard to measure, they've got short lifetimes, and some other factors like that. Keep thinking about how atoms exist and what particles make them up, and we'll see you next time.